Hello everyone, welcome to this lecture video tutorial in the mathematics of the modern world. Enjoy learning. Hello everyone. In this lecture video, we will be discussing about relations and functions, which is actually a continuation of our discussion in chapter 1, which is entitled Sets and Functions. So for our introduction, the the concept of relations and functions are visible in all areas or branches in mathematics. Why is that? If you recall your high school mathematics, like in algebra and trigonometry, or in pre-calculus, or in basic calculus, you encountered these words here: relations and functions. Maybe you did something like graphing, like getting the derivatives or integration. All of that stuff are discussed in high school mathematics. So meaning to say that our knowledge and understanding of some concepts in the previous lesson, this previous lesson mean that your previous mathematics, like sets, real numbers and their properties, intervals and interval notation of sets, basic algebra and trigonometry concepts, and so on, are badly needed here before going through in the ongoing discussion. So for our definition, first definition, let's define relation first before going through the definition of a function. So as you can see here, a relation R, our relation is denoted by a capital letter R. From a set A to a set B is a rule. The other term for a rule is govern. Is a rule that assigns to each element X in the set A, which is called an input, at least one element called Y in a set B called the output. So what does this definition mean? This definition is what we call the verbal. This is what we call the verbal description. Verbal description of a relation. So what does this definition mean of a relation? Okay, it is like if you have a set A here, a set A, it has an elements. There are many elements in a set A, and then each object there, just imagine that it is mapped to at least one element in the set B. At least one, meaning to say, if for example in a real situation, the set A are judges and the set B are contestants in a pageant. Okay, we have judge 1 in set A, judge 1, judge 2, judge 3, judge 4, judge 5, and so on. And then in set B we have a contestant in a pageant, girl 1 or girl 2, girl 3, girl 4, So for example, this judge one here, judge number one, maybe he choose contestant number one, or the girl one, and the girl three, or the girl seven. There are, he choose three because it says here at least one element. Okay, at least one element in every object in the set A. Every judge in set A, he can choose more object in the set B, which are the contestants. Okay, in the pageant. Okay, that's what we mean by a relation. And notice here there is a very important word that you have to to analyze, is the word each element. Okay, that word is very important in the set A. Okay, what do you mean by each element? It must be that all elements in the set A has a must assign. You must assign all the elements. If there is an element in the set A that you did not assign, then that is not called a function, or that is not called a relation. If there is one element, only one element, example in set A there are 10 elements, okay, and then you assign every object from 1 up to 9, and then you leave only the 10th object you did not map, or you did not assign to the uh, to the object in the set B, then in that scenario, that case, it is not a relation, okay, nor a function. Okay, so I hope you figure out the illustration. Okay, then let's move forward. The set A here, is called the domain, okay, of the relation R, and the set B is called the codomain. Some authors, they did not put an emphasis to this word here, the codomain. I don't know why they forget to define this word. Okay, but in um, many prestigious books in math, they always define the word codomain. This is very important uh, definition. Okay, so don't forget our A is the domain, and our set B is called the codomain of the relation R. And by the way, there is an uh, important function of the word of the letter R here. So the usually in many books, they always denote the relation to be the capital letter R, and if there's any other uh, relation, they call it R1, R sub 1, or R sub 2, or R sub 3. But there are other books also that, as long as it is a capital letter, then, and it's clear in the discussion, then meaning to say there is a word relation before the capital letter, then that that association is a relation. Okay, so don't forget about that. And the last definition is the definition of the range. They always emphasize this. Well, actually, this is very important, more important in the codomain. Okay, the set of all y in B that is assigned to some x in the domain, okay, is called the range of the relation R. So what does it mean? So remember this illustration, the contestant and the judges. For example, in the set A, as I've said, all those the objects there are all judges, all judges, uh, judge 1 up to 10. In the set B, we have contestant 1 up to say 20. Suppose that all the judges, okay, choose contestant number 1, okay, and they did not choose contestant 2 up to 20. So notice the set A is the domain and the set B is all the contestant, but the range is has only one element, which is the contestant number 1, because it says here it is the set of all element y that is assigned to the values in the or to the object in the domain. Okay, so let's have an illustration for this. Actually, the verbal description of a relation is very hard to understand for some students, even me before. Maybe it is because the the definition is written in English language, or maybe it is very abstract in form, or maybe for some students they lost in interest in studying mathematics because it is math. So in order that for those students to visualize or to describe the function, the relation, I mean, it is very helpful to have a picture or a portrait of this definition, the definition of relation. So we can look at uh, the what do you call this one, the other ways to we can look into the other way of visualizing a relation by using the diagrams or mappings or arrow diagrams. You can also visualize it using, or you can describe it using ordered pairs. You can also describe it using table of values. And finally, you can describe relations or functions using equations. These are four these four ways are used to visualize or picture out or to portray or describe a relation or a function. So that they will be able to comprehend or digest the the definition or the idea of this definition here. Okay, so in order, I already give you an example about the judges and the contestants. Let's try another example by using mappings or diagrams or arrow diagrams. Okay, so when you try to visualize or to describe a relation using mappings or diagrams, it is usually written in this form. So example, if you have a set A here, this is your domain. Okay, don't forget this is your domain. Here, this is your codomain. So let us again have a simple illustration. So a relation from a set A to a set B, we have a relation here denoted by R. And if you have an object here, as I've said, let's recall again the judges and the contestants. So if you have judge 1 here, judge 1, judge 2, judge 3, judge 4, judge 5, judge 6, judge 7. Okay, and then you have a contestant here, uh, contestant number 1. Okay, contestant number 2, number 3, number 4, number 5, number 6, number 7. Suppose there are 8 contestants. Okay, so before I said there are, I guess, 10 contestants and 20 contestants and 10 judges. So let's have this illustration. It says here, in the definition of a relation, each element, okay, this is very important, each element x. When you say each element, it could be uh, it could mean for every element. Is that clear to you? Okay, it says here, when you say relation, you allow it to, as you can see here, to have many partner. Okay, a relation allows one to many. Okay, remember that a relation allows one to many. Okay, so meaning, example, contestant judge number 1 is he choose, let's say for example, he choose number 2. Contestant number 2, he choose number 5. Contestant number 3, he choose number 1. Contestant number 4, he choose number 8. Contestant number 5, he choose number 2. Okay, contestant number 6, he choose number 5. And contestant number 7, he choose number 5. Okay, so all of the elements here, each element, okay, you must assign it. Okay, and it says further that, example, judge number 2, he choose again contestant number 1. Okay, so what did you see in this illustration? If there is more than one arrow in the object or in the element of the domain, like for this example, okay, if it allows more than one arrows, then this example is a relation. If it allows more than one arrows, because it says here at least one element. I hope it's very clear. Okay, what if example number 5, we choose again number 5. Okay, example number 1. Okay, as you can see here, there are 3 arrows. So when you say when you talk about relation, the object in the domain allows more than one partner. Okay, that's what we call a relation. Okay, and also please do remember that every element in the domain must have a partner. You must assign. If there is an element here, for example, there is an element like example like letter A. Okay, sir, this is irrelevant because this is of course a letter and we have a numbers here. Okay, let's change. Let's go back and let's have another number like number -2, for example. Okay, and this object here don't have a partner in the codomain, then this illustration or this given is not a relation. It is not a function also. Okay, if there is an object here that do not have a mapping. Okay, so I hope you put that into your mind. Okay, it is not a relation, it is not also a function. Okay, so let's erase this one. Okay, let's erase this. Okay, and we can see that, as you can see here, this is a relation. Okay, this is an example of a relation. So what color? Green. This is a relation. Okay, so to get the domain, this is the domain and this is the codomain. Okay, so our domain A has an elements 1 2 3 4 5 6 7, whereas our codomain, which is the set P, has the elements 1 2 3 4 5 6 7 8. The codomain must be all the elements in this set, whereas the range, okay, the range is are those objects in the codomain that has an arrow. Okay, it has a mapping. So the answer must be these objects here. Okay, these are the objects that has an arrow. Okay, so the range is 1 2 3 5 and 8 only. Okay, so as a remark here, the range is always a subset of the codomain. Why is a subset? Recall in your previous lesson, every object in the range are also an object or an element in the codomain. So a range is always a subset of the codomain. It's very obvious in the illustration. Okay, so that's what we mean by a, what do you call this one, a relation when you describe it using mappings, diagrams, or arrow diagrams. Okay, so we have letter A here. Let's try again to visualize a relation, subletter B here, using a machine diagram. Okay, this is what we call a machine diagram. This means that if you have an input x, okay, an input which is x, as you can see here in the definition, okay, look at the definition, an input. Okay, this is our input. Okay, our input, okay, this is our input. Then you have the output. Okay, so what you will see here is that you have an output which is y. Okay, and we have here a machine. Okay, something like this. This is our relation R. So you can imagine that this is our output. Okay, output. Okay, this object here are element of the domain, whereas the objects here are called the output, which is the element of the codomain. Okay, so this is our input and this is our output and this is our machine. Okay, just imagine it that way. Okay, so as I've said before, we have a remark here. A relation allows one-to-many correspondence. Okay, one-to-many. There is an object here that allows one-to-many. So that's what we call a relation. And also the range, as I've said, of the relation is always a subset, okay, of the codomain of R. Okay, so please remember that. So what do we mean by a function? This is just a negation, or okay, the negation of the relation, meaning to say if it allows one-to-one correspondence, okay, one-to-one correspondence, then that uh, uh, definition is what we call a function. Okay, if it never allows one-to-many, meaning one-to-one, every object here, there is always an object here, one object that you are going to map. Okay, so if you look at the definition, it's just the same, but here our notation is small f. For the relation we will be using the capital letter R, but in the function we will be using small letter like capital small letter F, G, H, and sometimes big capital letters, but not the the letter R. Now we reserve that for the relation. Okay, so look at here again. It says here that each element, okay, to each, meaning to say it's just the same as the relation. All of the objects in the codomain must have a mapping, but there is a very important phrase here: own one and only one element. It doesn't matter if all y's, all x's, all objects in the the domain, they choose only one element in y, as long as there is only one arrow. That's what we mean by a function. Okay, so let's have an illustration here. Let's illustrate. Let's copy this one and then paste. Okay, let's try to visualize a function here using a diagram again. Okay, let's copy this, copy and then paste. Okay, sub here. Okay, so again we have a set A and then a set B. This is codomain. We have a mapping which is denoted by small f. So what are we going to do here? Let's color blue. Example, we have 1, -2, 7, 3, and 5. And here we have A, B, C. Okay, the object in the domain and codomain are not always a number. Please remember that. There are times that you can put a fruit because it is a set, or a car, but for a simple illustration, let's try this. Let's have this example. So a function says here, it must have, you must assign each element. Okay, so let's try color this one, purple. Okay, so it says here one and only. Okay, maybe you have that one or that one or that one or this one. Okay, I purposely not put an arrow in this object. Okay, so in a function, remember that there is only one arrow. Okay, only one arrow. Okay, because it says here one and only one element of the set B. Okay, so there is a big difference in the definition of a relation and a function. Okay, because a relation allows one to many, but the function never allows one to many. Okay, that's the difference between a function and a relation. Okay, so later, if you have an equation and then you graph that equation, there are several ways on how to uh, picture out if the function or the graph of that function is a relation or a function. Okay, so I know it's this is very easy to understand. Okay, so we have a reminder here. A function, we will denote it by uh, small f or small g or small h or big F or big G or big H, etc. Okay, why is that? Okay. Remember that the relation, we reserve the capital letter R for the relation, but here we will be using this notation. But if there are others, uh, example 1 2 3 4 5 6, there are 6 of them, and then you have the 7th function or the 8th function or the 20th function, all you have to do is use a subscript, f sub 1, f sub 2, or g sub 1, g sub 2, and so on and so forth. Okay, so but again, if there's no confusion, uh, the author writes writes this way. For example, the function f, then automatically that the function m, automatically the m is a function. Okay, so it depends upon the author. Okay, but in our discussion we will be using this symbol, or maybe in your module you will find some other notations. That's not a problem. There's a word etc here. Okay, then also in the reminder number 2, in the function, uh, the range is denoted as this one, d sub f, while the range is denoted by r sub f. Okay, so meaning to say, in this illustration, in this example, this is a function, this is a function. Okay, in this example, the domain of the function yf, because our notation here is f, if this is g, then we have d sub g, if this is h, then this is d sub h. Okay, is set. Okay, 1 -2 7 3 5. Okay, it doesn't matter, you can rearrange that because it is a set. Okay, the range is r sub f, which is a and c only. Why? I've discussed this earlier, that the range are those objects in the domain which are mapped by the element or elements of the codomain. The codomain is A, B, and C. Okay, and note that the range is always a subset of the codomain. Okay, that's the difference between the codomain and the range. Okay, in the succeeding discussion, there will be a loss of information if you will use the other method, like the ordered pairs and the table of values, or the tabular description of the function or relation. Okay, so I will remind you for that later. Okay, that's the meaning of the relation and the function. Okay, the other way, before I forgot, uh, there are other books that, okay, there are other books that they write this one, the arrow diagram. This is an arrow diagram or diagrams, the same. So there are other books that the denote it this way. They have a visual a diagram like this one that I'm going to write here. Okay, so for example, if you have a diagram like this, okay, this is your A. Okay, sorry, this is your A, this is your domain, then this is your codomain, then you have a mapping here. This is your R, this is R1, okay, R sub 1. If you have an object here like X, or another object here like A, or another object here like P, so if there's an object here like this is 1 2 1 2 4 7, example, if you map X to 1, okay, then 1 is written as R sub 1 of X, okay, meaning to say if you are given an equation like this, okay, meaning that your X here is an element of the domain, and your machine or your relation is denoted by R1, and it is mapped to the object in the set B, which is what we call number 1, or this is our Y, okay. So another example, if you have A is mapped to 4, then your 4 is R sub 1 of A. The same discussion or explanation in this in the previous one. Your object A here is in the element of the domain, and your rule or your machine is R sub 1, and it is mapped to your object A here is mapped to 4. So if you are given an example like this, then this means that your A is mapped to 4, okay, using the machine R sub 1. So another, for if you have B, this one, this is R sub 1 of B. So your R sub 1 here will vary if your notation here is another letter, like you say if this is M or N or whatever notation, okay. So this, do remember of this scenario also, okay. So our domain is XAB, our codomain is 1247, but our range is 147 only, okay. So for the second way, which is ordered pair, this is also a way on how to visualize or to picture out or to portray or to describe a relation or a function. You can use this concept, ordered pairs. This is very familiar in your high school mathematics. If you did you remember this notation, okay, do you remember this notation, okay. This is an example of the ordered pairs. I know you are very familiar with this, but anyway, if you want to describe this what do you call this one, this example or illustration using an ordered pair, then you can write it this way, okay. Let's put a boundary, okay. Let's put a boundary here, okay. Our sorry, let's try another color. like blue. Okay, okay, it is an ordered pair. We have 1, I forgot, 2. Let's complete the list. Okay, let's try to recall. R1 is mapped to 2. Your object 2 here, element 2 here has 2 mappings. So we are going to put 2 here, and then let's complete the list. 1 to 2, 1 to 5, 1 2. Okay, let's try another color. Let's try this one. 1 2 2 1 2 5, and then 3 only 1, and then 4 3 and 4 has only 1 partner. 1 8, 5 has 3 partner. Okay, 5 has 3 partner. Okay, so we have to put a boundary here. Okay, 1 8, let's see, sorry, 1 8 1 8, and then we have also 5 as 3 partners. What are the partners of 5? We have 1 2 and 5. 1 2 and 5. Okay, 1 2 and 5. 1 2 and 5. Okay, for this element 6 and 7, I believe that there is only 1 partner. So for 6 we have 5, 7 is 5. Okay, so that's all. 7 and 5. 6, sorry. For the element 6 and 7, we have the same partner. Okay, same mapping. And notice that there is an equal sign here, and our notation is R. Okay, our notation is R, so we have to put R here. R. Oops, sorry. Let's try. Okay, so this is how you are going to describe the relation using diagram. If you transfer it to an ordered pair, this is what it looks like. Okay, so what happened in the concept of ordered pairs if you describe the relation using ordered pairs? If the given is in the diagram, and you are going to transfer to visualize or to describe the diagram using an ordered pair, there is what we call a loss of information. Okay, sometimes uh, sometimes there is a loss of information of information if you use the idea of uh, visualizing uh, so there's a loss of information because the idea of visualizing the relation as a set of ordered pairs. Why? As you can see here, you can only recover the domain and the range. You cannot recover the uh, codomain of the given. Okay, so as you can see here, 7 is cannot be found. Okay, 1, look at the second coordinate, 1 2, we have, okay, 3 is missing, 4 is also missing. Okay, what other elements of the codomain? 3 4 6 7 is missing. 3 4 6 7 is missing. Okay, so please do remember that. Okay, so if you are given uh, an example or a question in the form of an ordered pairs, then automatically the you can extract the information, only two information, the domain and the range. You cannot uh, recover the codomain of the relation or the function. Okay, so this is the one of the what do you call this one, um, failures, no, in converting diagrams to ordered pairs, or if you want to transfer or to visualize ordered pairs to diagram. Okay, why is that? Because if you will visualize this using diagram, so you have to create an oblong here and then put the elements x, put the domain, and then put the values of the range. But as you have noticed, you cannot uh, visualize, or you cannot get the information of the codomain of the relation or a function. Okay, so that's the problem in using in describing or visualizing the relation as a set of ordered pairs. So I hope you have an idea. And also in the mappings, or if you want to describe the relation using mappings or diagrams, there's also a problem um, with this what do you call this one, illustration. Okay, or yes, this illustration. The problem is that uh, this is this is too small. What if your set is, what if your domain is infinite? Okay, what if your domain is infinite? What if your codomain is infinite? So there's a problem of visualizing a function or relation if you use a diagram or a mapping. Okay, this will you have a big illustration or big circle or oblong to put all the objects in the codomain or in the domain. So this is also one of the problem using a diagram. Okay, so for the third one, using table of values, number 2 and number 3 are the same. There is also a what they call this one, a loss of information. If you want to write this the previous example in the diagram, you want to write it as a table of values, then you can express it this way. Okay, for example, we have x and this is your y's. Okay, so we have 1 2 3 4 5. How many order are, sorry, I think there are two twos. Okay, then 3 4 and then 3 fives, 1 2 3 and then 6 7. Okay, so 1 is mapped to 2. Sorry, let's try another color. We have 2 1 5 1 8 1 2 5 5 5 1 2 5 5 5. Okay, so okay, I remember something. If you are given an ordered pairs, how would you know that it is a function or a relation? Okay, so notice here that if the first coordinate is repeated, okay, like this one, the first coordinate is repeated. Okay, the first coordinate is repeated, then this set of ordered pairs is a relation. Okay, so if you are given an example or a question later, then if the first coordinate is repeated, then it is a relation. Also, in the table of values, the idea here is the x. Okay, the domain is repeated. Okay, as you can see here. Okay, it doesn't matter in the codomain. Okay, doesn't matter. So but before uh, I move to the last method or way on how to visualize the function or relation, as you see in the previous discussion, we talk about the last one is all about equations. Okay, let's have some note here. Okay, let's have some note. Let's try let the color green. Okay, let's put a note here, or shall I say a reminder. when we talk about a function described using ordered pairs, please remember this. Okay, it is defined as a function uh, from a function, let's say a function h from a set A to a set B uh, is a relation uh, from uh, from A to B, for which no two ordered ordered pairs have the same first components. Okay, so I've said it before, if all the first coordinate are distinct, no repetition, then that sets of ordered pairs is a function. Otherwise it is called a relation. So remember always that a function is always a relation. Okay, a function is always a relation, but not all relation are functions. Okay, a function is always a relation. Okay, so please do remember that. Some books they define it this way. Okay, they uh, define the function and relation using the set of ordered pairs. Okay, for this last visualization or on how to describe a functions or relation, this is using equations. Okay, before I will describe or visualize or to visualize functions and relay or relations through the use of equations, let me go back to the ordered pairs topic. I want to write the definition of relation and explain to you how it works. Okay, because as you can see in our previous discussion, I put a note here on how to visualize functions uh, using the set of ordered pairs or the concept of ordered pairs. Okay, I want you to know that this note here this is an alternative definition, which is most likely most mathematicians are defining the relation and functions through the use of ordered pairs. This is an alternative definition using ordered pairs. Okay, so I already defined the function using ordered pairs. I want also to define relation using ordered pairs. Okay, a relation, let's color blue. A relation, sorry, R, um, capital R, from a set A to a set B is a subset of A cross B. We already explained this notation in the previous video, for which every element x in the domain corresponds to an element y in the codomain. If your ordered pairs is an element of the set R. Okay, so let's have a quick illustration. Let's use our previous example, this example. Okay, this example, we will use this illustration or example to visualize or to explain to you the definition of relation and functions using ordered pairs. Okay, so we have one. Okay, one, that's correct. So notice that our domain is from 1 to 7 and our codomain is illustration. Let's have an illustration here, color black, illustration. Your A before is 1 up to 7, 5, 6, 7, and our codomain is 1 up to 8, 5, 6, 7, 8. It says here in the definition, our R is above. Okay, our R, let's say our R here is this one. Let me put, okay, that's our R. Okay, don't forget about that. So it says here that we have to form the Cartesian product of the set. Okay, so what is A times B? Okay, our A times B is, as you notice in the previous discussion, you can have this one and so on and so on and so forth. Okay, 2 1 2 2 and so on. Okay, this is 1 1 1 2 1 3 1 4 and so on and so forth, up to the last three elements of the Cartesian product is this one: 7 6 7 7 7 8, 7 6 7, this is finite, and 7 8. And as you have noticed, there are how many elements? 7 times 8, 7 times 8, 7 times 8, we have 56. Okay, 56 element ordered pairs, ordered pair. Okay, all in all in this set. Notice in the definition says here that every x, okay, every element x in the domain, this one, So our x's here are 1, 2, 3, 4, 5, 6, 7, 8. Okay? No, up to 7 only. Okay? So these are our x. There are 7. Corresponds to a y in B such that y in B, so there, as you can see in the set R above, so our first coordinate are x's, okay, the second coordinate are our y's, okay. So meaning to say, just locate all these ordered pairs in the set A times B, and it says here in the definition of relation, it is a subset of A cross B. So meaning to say, all these ordered pairs must be an element of A cross B. So let's try 1 2 2 1. 1 2 and 2 1 are of course here 1 2, and you can have 2 1 here. 2 1, where let's have color blue. 2 1 here. We have 2 1. Okay. We have 2 5 3 1. 2 5. We have 3 1. Okay, so every element of this set, okay, every element here are also an element of A cross B. That's why a relation is a subset of the Cartesian product A times B. Okay, so this is the definition of relation using the set of ordered pairs. The same is true for function, as I've discussed in the previous lesson. Okay, it says here, let me remind you that if you have no two ordered pairs, meaning to say the first component, every first component of the ordered pair must be distinct, no? So you should not find an ordered pair that have the same first component in order for that set to be a function, for that for in order for that set to be a function. Okay, that's the difference between function and relation. A relation allows a repetition of the first coordinate. Okay, so I hope that's clear enough. If you will use the idea of, or to visualize a function or relation using ordered pairs. Okay, so I'm sorry, I have, as you can see, last time I recorded that video last night. I have a red shirt, and for now I have, that's a uniform. Okay, so I have to change clothes, and this is color blue. Okay, so for now, let me formally discuss the idea of equations. In using equations to describe relations or functions, one must be cautious here, because this topic is really hard to understand. It's really hard for the student to comprehend this topic using, when you are trying to describe relations or functions using equations. In this topic, students are having hard time to 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 find, or to how to get the domain of the relation or function, to find the range, to find the codomain, and many other stuff related to this topic. But as you can see, I will try my best as your instructor, your teacher, to explain to you, to make this topic easy to understand. So with this, let's have an illustration. You are familiar with this word. okay, equations. So for example, if you are given an equation like this, 3x squared minus x plus 2, okay, this is an equation, okay, because you can see there is an equality sign. In this way of describing a relation using equations, I put it in the definition of the relation before, that we will, as you can see here, let's recall the definition of the relation, the verbal description of relation. As you can see here, I put a note. When we consider relation or function, the sets, the domain A and the codomain B, we usually use the set of real numbers to associate the set of real numbers for the domain and the range of the codomain of the relation or function. So here, okay, in this note, A here is usually the set of real numbers, and the codomain is also set of real numbers. Otherwise, in the given or in the problem, if the domain is something like other set, then we cannot do with that. Just stick to the question, okay. So if, for example, there is no mention of the sets A and B, then we usually take the domain or the codomain to be the set of real numbers, usually, okay. So as you can see here, why do we have to take the domain to be the set of real numbers, okay? This is because in order for this equation to have a meaning, we should put the value of the variable must be a number. You cannot put a meaning of this variable here if you will use other objects or other things. There is a meaning of this equation if you put a number, okay. For example, if you put 2, then there is a meaning when you have 2 squared. 3 times 2 squared minus 2 plus 2. So there is a value, okay. It is well defined. However, if you will use other objects like apple, then you cannot put a meaning when you replace x by apple. We have apple square, so there's no meaning to that, okay. 3 times apple square minus apple plus 2, then this equation is meaningless, okay. So there are several notations that I am going to write here. Sometimes in other books, okay. Let me put here in other books. you can find this notation. They write it as this one, 3x squared minus x plus 2. If your function is denoted by f, then you will use this notation, small f. But if not, example, if they use letter G, small g, then you will use G. Okay, and let me have to put a symbols here, some symbolism. Okay, symbolism. In describing equations or relations using equations, you may find this notation in other books. This one, okay, or you can find this notation. Okay, this means that your variable here, notice the symbol. Okay, notice the symbol. We have this is a long arrow, but this is a long arrow, but we have this bar here. Okay, so this is just as before, this is f of x. Okay, this is f of x, meaning your x is mapped to y and your machine is the variable f. Okay, so your machine is the variable f. Okay, so please take note of this notation. This is very familiar notation. You can also find you can convert this equation to this notation, or to this notation we can go back to this this familiar notation of equations. Okay, or in some other books you can find it this way. If you have this one, you can rewrite also this way. A set of all ordered pairs where your what is this notation? Y is equal to 3x squared minus x plus 2. Okay, so this symbol also this notation, you can convert this to this notation here. Okay, you can transfer this notation of a function or relation using this symbol. Okay, so as you can see here, the question is, as I mentioned in a while ago in the introduction of this topic, equations, I've said that students are having hard time finding the domain of the relation or the function. Okay, so the question here is, what is the domain or range of the function f? Okay, so the answer for this is if there is no mention of the sets A and B, the domain and the codomain, usually, as I've said before, we usually take the domain A and codomain B to be the biggest set in the set of real numbers of values x, meaning element, for which y is well defined. Meaning to say, as I've explained before, this equation has a meaning if you replace the variable x to be a number. Okay, there's no meaning if other meaning if you use other objects or elements of the set of the domain. Okay, so let's focus on the set of real numbers. There are other objects like matrix, or it could be functions, or it could be other objects in higher mathematics that you can put a meaning to this equation. But for now, let's focus on the set of real numbers, because as you can see, if you are given an equation, you can graph it, you can illustrate this using the set of ordered pairs, using diagram, or using tables. You can convert this equation to the other way of visualizing a function or relation. So as I've said, it says here that the value of x should be in the set of real numbers, and when you substitute a value, it must be that the equation is well defined, meaning if you put an x here, there must be a y. Okay, that's the answer to the question, what is the domain or the range of the function f or the relation f. Okay, so but there are equations that are hard to get the relation, the domain and the range. For example, the radical equation, the rational equation, and many other functions or relations that we will discuss later. Those equations are hard to find the domain or the range. However, if you put it in your mind, this phrase here, this one, okay, all you have to do is to get the biggest set in R, okay, for which the get the values x, just get the values of x in R for which the y is well defined. Okay, so just put that idea in your mind, and then everything will be easy. Okay, so let's have a method on how to or steps on how to find the domain of the function. So these are the steps steps on how to find the domain of the relation or the equation y is equal to f of x. Okay, remember that this notation depends on the problem. Okay, but usually we use x and y, but this notation f, it depends on the problem. If the problem is use the notation f or g or h or big F or any other, then all you have to do is to replace it. Okay, so step one. So the first step is to solve the equation for y in terms of x. Okay, what does this mean? This means that all the x of the equation must be on the right hand side. Okay, sorry, where is that one? Okay, all the x must be on the right hand side. Okay, when you solve the equation for y in terms of x, all the x's must be on the right hand side and dy must be on the left hand side. Okay, so that's what we mean by y in terms of x. This is what we mean by y in terms of x. And also for it to be easy, the coefficient of the y here must be 1. Okay, and then the exponent must be 1. But if not, then that will be a more complicated equation. Okay, but usually in this subject, we will be the y here must be 1 and the exponent must be 1. Then the x here doesn't matter if it is irrational, radical, or degree 1 or degree 2, it doesn't matter. Okay, for step 2, this is now the idea here. Okay, you have to determine the biggest set in R for which y is well defined. So determine the biggest or largest set of values of x for which y is well defined. We already know the meaning of well defined, meaning to say it is distinguishable, it is clear. Okay, clear to understand. That's the meaning of well defined. Because as you can see here, let's go back. If you replace x by apple, then it is not clear. Apple square has no meaning, or tiger square, or any object, real object, of course. But if you use matrix or other things in mathematics, higher mathematics, then of course there will be a meaning to this. Okay, but since you are most of you are not mathematics student, then let's focus on the set of real numbers. Okay, so it says here that after solving y in terms of x, you are going to determine the biggest or the largest set of values of x for which y is well defined. Usually this will be a what do you call this one? This is an infinite set. Okay, so just like before, this one, if you put any value of x, okay, if you put any value of x here. Then this x, which is a real number. Okay, a real number. Do you know what is a real number? The set of real numbers. This one, this notation. Okay. Let me recall that. Let us recall this set. This one. This is what we call the set of real numbers. Okay. I've mentioned in the introduction that you have to recall your high school mathematics. Okay, the set of real numbers is defined using the interval notation, negative infinity to positive infinity. Okay, all numbers except complex, of course. Or if you want to visualize this set using interval notation, what do you call this one, using the diagram. Example, this one. Okay, this is the Cart's way of visualizing the set of real numbers. Positive infinity, negative infinity, we have 0 here. Okay, this one, 1, 2, 3, 4, and so on. Negative 1, negative 2, negative 3, and so on. So when you say the set of real numbers, all numbers in this is what we call the real line. Okay, this is what we call the real line. Okay, all numbers here, you can name it. You can name all those numbers: 1/2, 1/4, fractions, rational numbers, integers, and so on and so forth. Okay, non-terminating decimals, terminating decimals. All those numbers are example of a real number. So meaning to say, if you go back to our question, if you are given this equation, okay, and you are asked to find the domain, okay, this equation, okay, 3x squared minus x plus 2. Is there an x or a real number for which the right hand side is not well defined? Can you find an x, a real number x, for which the right hand side is not well defined? Of course you cannot. When you substitute all those real numbers from negative infinity up to positive infinity, you can always find y. Example, we have 100, 3 times 100 square minus 100 plus 2, or you put a 0, or we have put the square root, cube root, and so on and so forth. So if you put a real number here, then this is always well defined. So this is why this equation, this is a quadratic equation. This is very familiar to you in your high school mathematics. This is an example of a quadratic equation, quadratic function. Okay, quadratic function. This is always well defined for all real number x. So that is why the range of this, the domain of this equation is the set of real numbers. So remember that this is y in terms of x. Okay, because we already separate all x on the what we call this one, on the right hand side, and all y's are on the left hand side. Okay, so this is how to find the domain. Okay, so of the equation. Okay, so as an example, let me repeat it again. Y is equal to 3x squared minus x plus 2. The domain here if we denote this as f, mapping from this one x plus 2, then your domain here is the set of real numbers. Okay, so how about the range? Okay, so but before that, let's try another example. How about this equation? Y is equal to square root of x. Okay, and if you write, if you use a notation like this one, square root of x, then our domain is the notation of our domain is d sub g. So ask yourself, uh, is this y in terms of x? Okay, is this y in terms of x? As you can see here, all x's, you cannot find an x on the left hand side. Okay, so all x's are on the right side, all the y's are on the left side. So this is y in terms of x. Okay, this is now y in terms of x. What happened? Okay, so I think I double click. Okay, so it says in the we are done with step 1. Okay, step 2 is to determine the biggest set or largest set of values of x for which y is defined. So in the set of real numbers, if you substitute negative numbers in our x here, example, if you have negative 1, okay, so y is equal to negative 1/2 or negative 3. Okay, then all the numbers here, okay, all the numbers on the left side of 0, use your calculator. So what happened? It says that in the calculator you will get syntax error. Okay, you will get syntax error, or you will get an error. Okay, or you will get you cannot find undefined in the denominator in the calculator, but these things here is undefined. Okay, this is undefined. However, if you have an x which is starting from 0 to positive infinity, then this expression here has a meaning. Square root of 0 is 0, square root of 0.1, you have use your calculator. Square root of 1, square root of 5, square root of 1/2, and so on and so forth. All the values of x for which this equation is well defined is all numbers from 0 up to positive infinity. So this is why the answer for this equation is the set 0 to positive infinity. Okay, so I hope this is clear enough. Okay, I guess let's have another illustration, a complicated one, like example number 3. This one, example number 3. Let's have more examples to illustrate. Example, we have this equation, y is equal to, let's have a rational, 3x plus 2 over 2x plus let's say 2x plus 5. Okay, this equation, suppose that we define it to be h. Okay, doesn't matter, I choose h, so therefore we will use this notation. Okay, 3x plus 2 over 2x plus 5. Okay, so our domain t sub h is what? Okay, let me explain this. Is this equation y in terms of x? So clearly, as you have noticed here, all x's are on the right hand side and all the y's are on the left hand side. So this is y in terms of x. We are okay with step number 1. So for step number 2, you are going to determine all values of x for which y is well defined. Okay, so notice in the real line, if you put 1, let's say let's pick a number on the right hand side of 0, you have to put 1. 3 times 1 plus 2 is 5. 2 times 1 plus 5 is 7. So we have 5 over 7. So from here, you can see that 1 is mapped to 5 over 7. There is an association of the number in the object in the domain, which is mapped to 5 over 7. So if you use 5, so let's skip number 2, 3. Okay, but you can do that. Okay, let's use number 5. 5 times 3, 15 plus 2, 17. Okay, 17. 5 times 2, 10 plus 5, 15. So 5 is maps to 17 over 15. And as you have noticed here, all the values here, including fractions, including non-terminating decimals on the right hand side of 0. As you can see here, right hand side of 0, all values of x, this is always all values of x on the right hand side of 0. This is always well defined. And also for on the left hand side, you may notice that it is also in that way. However, this is a rational equation. Okay, a rational function. And notice that this is a fraction, and since this is a fraction, there must be a value of x for which the denominator is 0. Okay, here. Okay, so what is that value? Okay, what is that value? Usually, if you recall your high school mathematics, in order for the denominator to be 0, all you have to do is to solve it. Okay, you have to equate to 0 and then solve for x. Okay, that's the usual way on how to find the zeros of the denominator. Okay, so if you solve this, you can have x which is equal to negative 5 over 2. Okay, so this number here is somewhere in this interval. So negative 5 over 2 is 2 and 1/2, negative 2 and 1/2. So this is somewhere here. Okay, this is negative 2 and 1/2, between negative 3 and negative 2. Okay, so it's really hard to to find the zeros of this equation, since it is a rational function, okay, or equation. So if in case that you will encounter this kind of equation, all you have to do is to equate the denominator to 0, and then after that you have to include. So remember, all these numbers here from negative infinity up to positive infinity are candidates of this equation. However, only one do not have a mapping. So meaning to say, your negative 5 over 2 here is not well defined. Okay, not well defined. You cannot find a y in the Codomain such that you can associate negative 5 over 2. Okay, so meaning to say, our answer here is all numbers, all real numbers, and then we have to exclude negative 5 over 2. Okay, so that's how you are going to find the domain of the rational equation. Okay, so maybe let's have another illustration, a complicated one. Okay, let's have a complicated equation.